Okay, let's talk about equilibrium. Definition of equilibrium is, because it's when a chemical reaction and its reverse reaction are proceeding at the same rate, meaning we are creating product and we are creating reactants at the same rate. It is not the same amount, it is the same rate. Okay, and that can sometimes be confusing. So what we're talking about, if we look at this example, I've got dinitrogen tetroxide. Okay, as this heats up, that produces 2 moles. For every 1 mole of the dinitrogen tetroxide, I get 2 moles of nitrogen dioxide. Okay, and this is the brown color that you see. Over time, what will happen is I will generate enough of this nitrogen dioxide, and actually from the very beginning, some of this some of the nitrogen dioxide will go back and form the reactants. And at a certain point, the amount being produced is equal to the amount that is decomposing. Okay, it is not the amount that is present, it's the rate at which it is being produced and the rate that it is decomposing, but the amounts present can be very different. So, if we look at this graph, I've got rate on the y-axis and time on the x-axis. If you remember, the equation that we're working with is the dinitrogen tetroxide gas forming 2 moles of the nitrogen dioxide gas. Remember from kinetics, the rate going forward is going to be equal to the rate constant in the forward direction. That was supposed to be a K, and that is an F, times the concentration of the reactant, which is the dinitrogen tetroxide. Okay. The rate in the reverse direction is equal to the rate constant for the reverse direction times the concentration of N nitrogen dioxide squared, remembering that because this being an equilibrium, it is happening back and forth, meaning it does happen in one step, meaning that these are elementary reactions. Although it can be a mechanism behind it, you can write these equations that way. All right, so as the reaction proceeds, okay, this is a rate in the forward direction, rate in the backwards direction, and they will, when equilibrium is reached, the rates are the same. Now, we can contrast this with the graph of concentration versus time. If you notice, in the beginning, all of my reactants, I have my starting point for the amount of reactants. I don't have any product. As the reaction proceeds, my concentration of my products increases, concentration of the reactants decrease. At equilibrium, the amounts of the two stay constant, but they are not necessarily the same. Okay? But the amounts of products and the amount of reactants stay constant at equilibrium. And this is just a summary of those two. Take note what the axes are: rate versus time for the top graph and amount versus time for the bottom. At equilibrium, the rates forward and reverse would be the same. just goes into it. Another graph. The only difference with this graph is that we try to highlight the difference in the rates. When the reaction first starts off, only have reactants present, so it will only go in the forward direction until I make some product. If you look here, this is the smaller arrow. Okay, I have some B, and some of that B, that product, will go back and make the reactant, but at a smaller rate than what is being made in the forward reaction, until eventually I get to equilibrium, where these arrows being the same length indicate that it is equilibrium. The rate for the reaction going forward is equal to the rate going backwards. There are 5 characteristics of an equilibrium state that need to be memorized. All right. One is that it is a dynamic equilibrium. What the dynamic equilibrium means is that both of these reactions are still taking place. Okay? Product, I should say reactant still making product, product making reactant. Okay, so you have both reactions taking place. It is not static, meaning that all of the product stays as that. They go back and forth. It is also a closed system, meaning there is no exchange of matter with the surroundings. Neither the product nor the reactant can leave the system. So if it's a gas system, you got to have a lid on it. The concentration of the reactants and the concentration of the products are constant. Interestingly, there is no change in the macroscopic properties. Okay. Now, this means color, density, any other observable properties do not change. Okay, so this means, say if I have solid, the amount of solid present, oops, and my pen's all going to go away. I don't know what I did. Sorry, guys. Okay. So for this macroscopic properties, the amount of solid will be constant. That's B. Okay. But it may change shape, and we'll talk about that in class. And then the last point, point 5, is that equilibrium can be reached from either direction. So you can start with reactants, or you can start with products, or you can start with a mixture of both, and it will reach equilibrium from either direction as long as all of the components are there for the reaction to occur. And this just shows that equilibrium can be reached from either direction in a graphical representation. Okay, so how do we write equilibrium? Well, we draw that double-headed arrow. All right, and it's really not a double-headed arrow. I shouldn't call it that. It is really 2 arrows. One indicating reactants are making products, and then the other indicating that the products are going back and making reactants. Terms used to describe a system at equilibrium. Sometimes we will have more products present than the reactant. And if that's the case, the equilibrium is said to lie to the right. If at my equilibrium I have a higher concentration of reactants, then the equilibrium position is said to lie to the left. Sometimes it's easier to say, in instead of saying that it lies to the right, say it lies to the product side. And then conversely, if it lies to the left, it lies, I don't know what is wrong with my pen, to the reactant side. Let's talk about the equilibrium constant. So for the equilibrium constant, we've looked at this before. Your forward reaction, you can write the rate law. For the reverse reaction, you can also write the rate law. Remember that you're going to use the coefficient for the power on the concentration of that. At equilibrium, remember rate forward is equal to the rate in reverse. Set those two things equal to each other. Rearrange them so that it is Kf forward over reverse. And this gives us, if you look at it, this is your products over your reactants. Okay? Remember that you have to have whatever powers are for the coefficient at the concentrations. Okay, so this equilibrium is really just using concepts in kinetics and kind of putting them together. So that value, Kf over Kr, becomes your equilibrium constant, represented by a Keq, and that is constant at a given temperature. So at different temperatures, your equilibrium constant will change. And we're going to find out what this equilibrium constant can do for us. Please keep in mind that the general representation for your equilibrium constant is your Keq. We can write a bunch of different K's. Remember, this is a capital K, different than your rate constant, which was a lowercase. Your equilibrium constant is sometimes written as Kc, sometimes written as a Ka, sometimes written as a Kb, sometimes written as a Ksp. So there are several different ways of being specific with a Keq. We'll also see that it can also be written with a Kp. All these have different meanings. We'll talk about a Kc and a Kp. So the general is a Keq, but all those others are equilibrium constants, and you would develop their expressions the same way. So if we look at the general equation with a little a, capital A, the lowercase letters referring to the stoichiometry, the stoichiometric coefficient, and the capital letters referring to the components or the chemical compounds in the reaction. The general expression is Kc, and then you can look at that, and again, it is products over reactants. So let's get some practice.